Okay, so good morning everyone again. Welcome to the 12th lecture on NLP with deep learning called Inference. So let's have fun today, okay? So today we're gonna touch research which is like 3 weeks old at the end. And this will be a nice wrap up of the whole course. So just, I think this is the last lecture, to be honest, because we have the exam in like 3 weeks or so. So I'll leave you some time to prepare for the exam. We'll have today the lecture and the exercise, and we might talk about the exam after this lecture. But we're gonna wrap up like content-wise. We're gonna really touch the sort of state of the art, like things that are actually being done. And it's like a huge and vast, landscape of research in there. So we're just, picking up a couple of things. But I think, what are we talking about today is something substantial, which is actually very useful and being used in all these models we're using these days. And I think it's gonna stay around for a while. So I think that's at least we should be talking about this in this lecture. So, and what do we mean by inference time, scaling, and reasoning? So what is inference time in the first place? Inference time means we do have a model which is trained and deployed, whatever. We do have a model, and you can prompt the model. That's basically we're running inference. So you prompt the model and get some results. What is reasoning? That's an interesting thing. So reasoning is, you might know, there's different ways, different descriptions of reasoning. As a humans, what is reasoning is like you're putting together pieces of information or some logical inference and end up with some answer. If you think about like logical reasoning, like in propositional logic, you have, I don't know, modus ponens rules, or you put rules together, and from implicit knowledge you actually make like something like explicit knowledge. And there's other types of reasoning, and like mathematical reasoning is like you put formulas together, and underneath there is some logic in there. So humans reason as well about things. If you're solving a problem, you kind of think about like the particular steps, how they work together, and things like that. So this is like a generic. We're not going to be talking about particular reasoning today. There will be different sorts of reasoning. Okay, make sense? Cool. Okay, so what we have talked about so far in this whole course, or like the main part of that, is we have large language models. LLMs, large language models. We might have like large language models, like big LLMs, whatever. So LLMs, it's a typo. And we talked about pre-training them from scratch. So in this like next token prediction thing, and you do this language modeling task basically. And then how do you make them useful is by, well, you can either do fine-tuning as for the early GPT models, GPT-1, GPT-2 maybe, or what you do then is also instruction tuning, which means you show them the task and how you want to solve this, like giving instructions, and you can also fine-tune the model on these instructions. So the model is not just continuing spitting out words, but it's actually solving the task you're asking for. So following the instruction, basically. And one of the things we talk about in the last two lectures, I guess, is the ability of in-context learning. So basically, you don't have to touch the weights of the model anymore. The model is already deployed. We're in this, in the inference time. And you just show a couple of examples of the task you want to solve, and the model will pick up the task and try to learn this task from these few examples, like the few shots. And but for this to work, you need really large models, like a huge number of parameters. So the small models, they don't have these, we call it like emerging capabilities or emerging abilities of the models. We don't have them. And the great example is zero-shot learning, where you just tell the model what to do and the model does it. It's like, this is the magic, where the magic happens. Anyways, so this is what we've talked so far. Okay, any questions? Does it ring a bell, most of that? So this is the starting point for today. Because even these big models, they struggle with unbounded multi-step computations, or some sort of reasoning, such as adding integers. So models, you can misuse the models for doing arithmetics if you want. You have a calculator, but why not use LLMs for that? But they, yeah, why not? As a research idea, not as a practical tool. Come on, But you do have them, and they can do stuff. But like, unbounded multi-step computation, it's an issue. Like, and this is a type of I would say like mathematical reasoning or like propositional logic reasoning, whatever you want to call this. Like adding integers, there's a clear procedure, there's multiple steps, but these are unbounded because, you know, how do you want to train a model on adding integers? Like you have some examples to show, but the model should like pick up how to do this by its own. And the thing is with the reasoning abilities, yeah, that's what I said. That's what I mentioned. Is these emergent behaviors, like emergent capabilities of LLMs. These models can actually have these capabilities of reasoning, and if they're scaled to bigger models, like over, I don't know, half a billion, like 500 billion parameters, maybe it's a good size, like the biggest models ever. And we can teach these models reasoning in even like in pre-training, but it really needs a lot of data. Just imagine, like what do we have to do to teach a LLM adding integers together? Can you train a model to add integers? So I'm assuming you can. So how would you do this? How would you teach a model to add integers? Like a standard, you have a model and you can pre-train it. How do you teach it to add integers together? Any idea? Yeah? Just as normal. Okay, so which means? Yeah, but then the model has to know it already. But let's assume the model doesn't know how to add integers. So how would you train a model to do anything? How do you train a model to do anything? Okay, so you have a loss, exactly. So what do you need for that? You need to show the model something.
And then you show the model actually the result that I can break from it.
Okay, yeah, you're getting somewhere. Yeah, you need some sort of answer. You need some sort of training data. You need to create a lot of training data. So how do you create training data for adding integers? You can synthesize data. How do you synthesize data? You write a Python code which says like, for any two integers, this is the input and this is the output, and you generate like 100 billion examples. This is your training data. Then you do the normal thing, like you pre-train the model, right? And I believe like you can teach a model to add integers. I'm almost sure. I mean, how well it will generalize to some like unknown territories of integers, that's a question. But you can teach this. The problem is, you have to pre-train a model on 100 million examples, and it costs lots of time and lots of money. I mean, like pre-training model on data, you have to have the machinery of GPUs, and everything has to fit in and so on. So this is actually very costly. So maybe there's other ways to do so. And that's what we're going to be touching today, is this inference time scaling. So we'll start with the history, which is a paper from 2021. It's called History now. So this paper, which I'll introduce in the next slide, they introduce something called a Scratchpad, which is, I mean, Scratchpad is a piece of paper you're just scratching, like writing notes on a Scratchpad, right? So like these big models, they suffer with reasoning, but the same models as before, they are able to perform complex multi-step computations, and they can do it even like in a few shot regime. So you can actually show a couple of integer examples to the model, and they can kind of pick up the reasoning. So they do have these capabilities. You don't have to pre-train them on like 100 million examples. You can just do few shot, and they will maybe pick up like how to do arithmetics. So, but they can do this in a very special way, because you have to ask them to perform the operation sort of step by step, showing the results of intermediate computations. So this is what this paper in 2021 did. It was, by the way, rejected from the iClear ICLR conference. You can find the reviews, and they're saying like, yeah, it's kind of boring, hard to reproduce, and it started sort of like this whole field. I believe it's one of these early papers on inference-time reasoning, inference-time scaling. So it's interesting also about research. Like some papers are not accepted to big conferences and are rejected, and they post it on archive, and then somebody will pick it up and just explore the ideas, and it will blow. Interesting. So what they did in this paper is they took a transformer, like I think some sort of decoder models or encoder decoder, it doesn't actually matter, to perform multi-step computations by asking them to emit intermediate computation steps into this Scratchpad. So what it actually means is, I mean, if you want to solve an algorithmic task, we simply add the intermediate steps of the algorithm, like adding integers. I mean, for adding integers, you might have an algorithm. I mean, what you learned at school is you start from the right position. Like if you have, I don't know, 81 plus 29, you start from these, so you add 9 plus 1 is 0, you have the carry on, and so there's an algorithm basically how to solve this, right? Do you agree? You can do it in your head, but you also like using an algorithm, I guess. You cannot just tell 81 plus 29 is 110. I mean, I had to count somehow. So there's an algorithm for doing this, and this is what you're gonna show the model. These intermediate steps of the algorithm as text. This is interesting. So you're basically showing a text how to solve this task, this algorithm. And then you can train the model to actually produce these intermediate steps as well during inference to the output. And they call this buffer the Scratchpad because this is just the intermediate steps. And what you do at training time, you will give the model the inputs, like, 81 plus 29, and plus the algorithm, like how do you solve this problem, exactly on these numbers, and you just train it as normal, like standard likelihood, next token prediction thing. So you basically supervise the model to solve the task, showing the algorithm of solving. And at test time, you will just get this. So I mean, I have an example on the next slide, which is just much more explaining. So this is the example of the input and the target for the algorithm of adding numbers. And as you may see, I mean, it's kind of cryptic, like 29 plus 57. So this is a text which you're putting into, this is the entire text which you're putting into training the model, right? You write it as a text, you write the algorithm as a text, and the model is trying to learn the whole thing. And from learning the whole thing, it's trying to generalize what the algorithm could be for adding some other numbers. And I mean, these are just comments. These are not part of the training data. But I think this is just the C0, C1. This is the encoding of the carry. Whether there is a carry, like you exceed 10 or not, you have to add +1 or not. And these are the intermediate results. So I guess 6, the intermediate result 8, 6, 0 to 8, 6, there's a carry, and this is the output. And then during inference time, you just put some other numbers, like, I don't know, 89 plus 29. And you want the model to generate all these things, including the answer. Okay, that's the idea. You want the model to generate not only the answer, but also to generate the algorithm, how it comes to the answer. And this, magically, in a way, it helps the model to actually reach the conclusion. Because if you just demodel, what is 29 plus 57 is 86, these model can do this, but will suffer. I mean, they won't learn the algorithm. They might understand the algorithm, but most likely not. So you can show them the algorithm, let them generate the algorithm, and by doing so, they will understand more the algorithm of solving the problem. Okay, questions? Does it make sense? Isn't it cool? Yeah, and yes?
So we're creating a data set
Yes.
for this.
Yes.
So we're doing the exact thing we don't want it in the beginning.
Yes, with the difference. So we don't want to just do like 80. So what we were discussing before was 29 plus 57 equals 86. We can do this. And you will get somewhere. I mean, it will maybe learn some additions of numbers. But now we're doing also explicitly writing the algorithm of solving the problem. So the reasoning, like how to solve this problem. And by doing so, the model will learn how to actually solve this thing. Like you give more guidance to solve the problem and generalize from this. Like it should learn that, there's something like carry, which is either 0 or 1 if you're over 10, and maybe I should do like the intermediate steps from right to left and so on. So you teach the algorithm now, the reasoning. So this is the difference, and it makes a difference in the results. Like now you are actually able to solve these problems. Okay? But I mean, this is just the beginning. This is just the beginning. Like the first paper on Scratchpad. So the disadvantage of this is they still have to fine-tune these models. I mean, you can generate 100,000 examples. You can generate this using some script, whatever. I mean, it's pretty easy to generate this, these examples by Python script or whatever. So you generate this, they generate 100,000 examples, and you have to still fine-tune the model. That was like the early papers. And of course, in their case, I don't know which models they used exactly. It was something like GPT-ish family, or maybe I don't recall exactly. But just look at the paper. And of course, these models were limited also in size. So they were limited by 500 tokens as the input size. So if you, or the generation window, basically, you can generate only 512 tokens. And I mean, for simple additions like this, you will fit into 500 tokens easily. But there might be problems which need like much more intermediate steps, and then you might run out of tokens to generate. So the tokens is the Scratchpad, right? I mean, you're generating the text, and after this, everything what you have here, this is the Scratchpad, so-called. These are the model's somehow intermediate outputs which it produces, and it helps him. It helps the model to find the answer. So the Scratchpad has a limited size. But it was cool because they used experimental long addition, some evaluation of polynomials, and even like Python code execution. So okay, I didn't put the example here, but just looking into this paper, they basically, you can basically teach a model to execute a Python code. You show each intermediate results of each line, what could be, I don't know, I should have put the example. This is kind of cool, but it's very big actually to fit a slide. So look into this paper, it's on archive, and you will see like you can do the similar thing as here, like you basically show what is the stack of the program and the variables, I guess. Like basically you build an interpreter in text, and you can teach a language model to execute Python code, which is kind of cool. Sounds silly, like why should you do this if you have a Python interpreter? But it turns out to be, very useful for many tasks later on. So they did this, and it improved the performance on algorithmic tasks. And what they said, a clear next step is to try to learn to use Scratchpad without the direct supervision. So they see the limitations of, I have to fine-tune the big model, okay? So maybe we should do it somehow better. So this is the chapter 1 of today's lecture, like going fancy, not fancy. I mean, I find it fascinating actually. So you can show the instructions of the algorithm, and the model will solve the algorithm. But still, now you have to fine-tune it. So what can we do about this? Is let's move to chain of thought prompting. So very efficient and at the same time very simple technique. So let's see. Okay. So their ideas of this paper, which is 2022 NeurIPS. So the reasoning abilities of language models, so we talk about reasoning, we know what it means. Of language models can be unlocked by a simple method motivated by 2 ideas. So they have these 2 simple observations. So the techniques for arithmetic reasoning can benefit from generating natural language rationales that leads to the final answer. Okay, so this is what we just saw. Like you can do this rationale, these intermediate steps that will help you to, to describe the algorithm, the intermediate steps of the algorithm, and it will help you to get the final answer correct, very likely. And the other observation is, so it was about a time when in-context learning basically hit, like GPT-3 was showing that we have this few-shot learners. So LLMs offer in-context few-shot learning via prompting, and we don't have to, so instead of fine-tuning a separate language model checkpoint for each new task, one thing is simply prompt the model with a few input-output examples demonstrating the task. So this is the standard prompting, or like in context learning, showing 1 example, 2 examples, and maybe like 0 examples. And they said like, maybe we can combine these 2 ideas. So how about we try to generate these rationales, these reasoning steps, not by fine-tuning, but just by few-shot learning. We can just maybe few-shot the model without having to fine-tune it, show these some examples, and maybe it will help. So here's is it readable? Okay. So here's an example of, so they compared a few-shot prompting and this new technique called chain of thought, few-shot prompting. And here's an example. So the model, so basically what you're doing here is you're putting an input to the model and you show, so this is like one shot in context learning. So you're showing one example of a task and the answer, and then you put another task and the answer. So the question is, Roger has 5 tennis balls, he buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? Okay, my brain explodes already. I mean, I could solve this problem, of course. Like it's a second grade problem, but you have to think about it. And the answer is 11. Okay, good. I mean, okay, I get it. So then the real question is, the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, okay, so this is minus. Okay, 23 minus 20 is 3. Plus 6 should be 9. I guess it's 9. Is it right? I mean, the solution to this. Okay. It's very early in the morning to do math. But anyway, so this is what you're asking the model. And you're saying, oh, okay, the answer is 27. I mean, this is wrong. Now we see this is wrong. I have no idea how the model came up with this. So, of course, I mean, the model has a hard time the model has to understand first the mathematics behind the description of the task, and then it has to also be able to compute the integers like very well. So what they do here is very easy, like having the idea of showing the algorithm, so to say. So we have the same examples. Roger has 5 tennis balls, blah blah blah, and now what they do in this in context. So this is still the in context. In context learning. Like if you showed examples, so they're showing the solution of the problem by actually showing the algorithm, like how do you compute the problem. So Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, so plus 5 plus blah blah blah. So it's 11, and then the answer is 11. So basically they plug in the solution of the problem here in words and show this as in this prompt. And now the model output is different because the model now knows it not only has to produce the final answer, but it has to also output, I'm asking for the intermediate steps to get this final answer, right? And the model is outputting the solution. The cafeteria has 23 apples originally. They used 20 to make lunch, so they have 23 minus 20 equals 3. Okay, that's what I thought as well. They bought 6 more apples, 3 plus 6 is 9. Okay, good. I mean, I'm as good as a language model now. And now, magically, the model, by producing its intermediate output, it's able to solve the problem. Like, why is it possible? I mean, that's a research question. Like, how the hell does it work? But just if you think about it, like the model is generating each token at a time. So at every step, it looks into the past, like you're here. It looks into the past and try to predict the most likely next token, and then the most likely next token, and then the most likely next token, and so on. So it generated all the text. So here, it has produced some sort of ideas, let's put it like that. And if it's producing the final answer, it can look in these intermediate ideas, which were produced by the model itself, and it navigates the model better to get the answer. I mean, of course, this could be wrong. I mean, everything can go wrong here. It's generation, of course. But you can, empirically, you get much more better results with using this. Like you want the model to do the reasoning while generating language, and empirically it helps the model to steer to the better answer. Okay, looks like magic, but it makes sense in a way. Questions? Isn't it cool? I think it's super cool. I think it's super cool. So I mean, of course, in this paper, who was that? Like Jason Wei and others from, I think it's Google Research. They didn't show just one example. Of course, it would be very hard just with one example, but basically the chain of thought, this is a full prompt example for some question answering data set. So obviously you test like multiple data sets, arithmetic data sets, strategy question answering. So here, this is the full prompt. You show at least 1, 2, 3, 4, 5, 6 pairs of question answers. So the model has a chance, but this is in context. You don't fine tune. This is just in context examples. So do hamsters provide food for any animals? Hamsters are prey animals. Prey are food for predators. Thus, hamsters provide food for some animals. So the answer is yes. So you see, like the model is pushed to provide these reasoning sort of thinking tokens in between before getting the answer. What's the performance of these models? So I think they compared to fine-tune GPT-3 with 175 billion parameters. Okay, it's a big model. Palm, if I'm not mistaken, was a Google model back in 21, 22. Very huge beast, like 540 billion parameters. It's still, I think, like from today's perspective, it's still a big model, like large language model. And the math word problem. So I mean, I will see this data set maybe in other papers today. So this is like some math questions. I mean, they are. I don't think if they're hard. I didn't check all of these, but some sort of these, additions and multiplications and things like that. Maybe much more complicated. And the results in solving these problems in math, from fine-tuned GPT to, I mean, of course, you have bigger model, but just and this is the standard prompting. You just show the answer. Okay, like, what's the solution to this problem? The answer is, and so on. So the model is not able to pick up, although it's super. I mean, it's a huge model. Like it's 540 billion model. It cannot do this, but just showing these in context examples in there with the chain of thought prompting, like you provide the solution to the problem, will give you sort of state-of-the-art result. I mean, it's actually very cool. So the properties of chain of thought are actually very attractive because it allows the model to decompose the multi-step problems into intermediate steps, and the additional computation, I mean computation in terms of, what can you do with these intermediate steps, like where is it stored? Yeah, you can basically just generate more tokens, and as long as you have the context for generating tokens, you can store everything into these generated tokens as intermediate steps. So you can sort of like dynamically almost allocate your room for bigger problems if you have enough context. That's the main idea. So this is sort of like the Scratchpad, right? I mean, you're generating tokens into some intermediate steps, whether you call it Scratchpad, whether you call it chain of thought. You're just generating tokens, and as many tokens as you can generate, that much intermediate reasoning things you can store into that, like internal thinking of the model, sort of. Okay, so this is, you can, distill the problem into multiple steps, which helps you to solve it better. The other question is, like, not a question, the other nice property is that you can sort of have an interpretable view into the behavior of the model, suggesting how it might actually arrive at the particular answer, right? I mean, if the model is outputting you this, oh, the cafeteria had 23 apples, original, and so on. So, I mean, it's an English text because you showed it an English text. So it's an English text you can read this, and you can, as a human, you can understand this, and one of the hypotheses would be, this is how the model actually solves the problem. Like, this is how the model sees the problem and understands the problem. And if there's a mistake somewhere, you can just spot it. If the model makes a mistake here, so 23 minus 20 is, I don't know, 8, then you see, oh yeah, I mean, the reasoning broke here, so the model couldn't do arithmetics or whatever. So it offers you some sort of like explainability opportunity, but that's a hypothesis, right? So you can make these models maybe more interpretable, maybe not. We'll come to that later. But at least you see something behind the answer, not just the answer is 27 and it's wrong. Yeah, it's like, okay, sure. Yeah, should I buy this model or not? I mean, no, not really. It's like, it's stupid. But if it shows you the reasoning, you might kind of trust the model more. That's an open question. Okay, so these are, okay, and the very cool thing now with this chain of thought is you can use it for math word problems, or for some common sense reasoning, or for some symbolic manipulation, and so on. You can use it actually now for any task that we as humans can solve via language. Because if you can decompose a task into like steps which you can describe in language, such as arithmetic problems, some reasoning here, I don't know, like a math proof. It's still like you can write a sequence of symbols, which is a language, so you can solve this task theoretically with chain of thoughts. I mean, you can use these intermediate steps of the algorithm. It can solve maybe programming languages problems or whatever. So this is kind of a nice property. Like it opens a window to like, oh, as long as you can do this, you can express it in series of tokens. Theoretically, it could be possible to show the model how to solve this problem and teach the algorithm of solving the problem. And the thing is, like, you can use chain of thought for any off-the-shelf, like just out-of-the-box LLM, simply by few-shot prompting. So you get any large language model for inference, and you just show the chain of thought with the examples. The only thing you need is like just a few examples of chain of thought, and it will work. There's nothing you need to pre-train the model for chain of thoughts. There's nothing you need to, I don't know, fine-tune or whatever. Nothing. It's just, if the model is big enough and can do in-context learning, most likely you can use chain of thought for that. So that's actually super fascinating. Okay. So far so good? Yeah, it's super fascinating, I have to say. Okay, so the question is now, just to recap, okay? So now we know, okay, so language models, they can do some intermediate reasoning. You can fine-tune them for the reasoning, and they will spit out the reasoning tokens, but fine-tuning costs money. Okay, so then you can maybe do few-shot prompting or in-context learning with few shots to show these intermediate reasoning, and that's even better because you can just use any model out of the box, and which is big enough, and that's good. But still, you need these examples in the middle. Somebody has to go and write, like, could Brooke Shield succeed at the University of Pennsylvania? I have no idea what it is. Let me say. Okay, yes or no? Hydrogen's atomic number squared exceeds number of Spice Girls. What the heck is this? Okay, no. How many Spice Girls were in the? How many Spice Girls were? 5, 4. Okay, some easy question. Okay, yes or no? Would appear? Okay, no. Well, just take this. I mean, you have to have somebody to write you this answer as a training example. Like somebody has to sit down and say like, hydrogen is an atomic number of 1. Okay, I think I could figure this out. 1 squared is 1. Okay, yeah, sure. There are 5 Spice Girls. Okay, I think I would fail on this. Thus, hydrogen's atomic number squared is less than 5. Like, imagine you're sitting somewhere and writing these training data. Like, it could be fun, but it's like it should be daunting. Yeah. Could a llama birth twice during war? Could a llama birth twice during war in Vietnam? Jesus, this is horrible. I mean, but it's kind of tough. Like, this is interesting. Could llama birth twice during war in like an animal? The war in Vietnam was 6 months. Okay. Really? Okay, the gestation period for a llama is 11 months, which is more than 6 months. Thus, a llama could not give birth twice during the war in Vietnam. So the answer is, okay, so you don't want to write these examples. Maybe you won't. I mean, it's kind of fascinating. Actually, I didn't look at these examples yesterday, but I find it's hilarious. Okay, so good. So far we needed these examples to show the model how to do the reasoning. The question is like, how many examples do we really need? Like 1, 10, or do we need some at all? And here comes the most hilarious paper, like I can tell, because you can get rid of all those things by just saying the model, just adding the prompt, let's think step by step. Period. Problem solved. You tell the model, you really write at the end of the prompt, let's think step by step, and you get, it will start outputting all these intermediate, algorithms in there, whatever, and it will get the answers right. You can get any model out of the box, which is good enough for in-context learning, which is like big enough, and it's capable of producing these intermediate outputs by itself already. Hilarious. So just so this is a 2022 again paper by a Japanese group, and just to the what do we need? Like a few-shot prompting. Okay, so this is what we had. Like Roger had 5 tennis balls and so on. The answer is 11. Okay, we saw this before. So the answer is 8, which is wrong. Okay, I get it. So then you might do like even worse, like 0 shot. Okay, what happens if you just show no examples? Like the answer is, you just show no example, so there is no example what you're kind of trying to solve. And of course, the answer, yeah, might be right or might be wrong. Okay, then what we are talking so far before was the few shot chain of thought. So we have the examples, and then we edit this intermediate explanation, Roger, blah, 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 explaining the answer, so that's what we discussed previously. And then it's spitting out the intermediate results and getting you some results. Okay, so far so good. And here's the trick. So you just zero shot. You don't need any training examples, zero shot. And you just put the question and say, answer, let's think step by step. And it's starting outputting just the intermediate steps. Okay, there are 16 balls in the total. Half of the balls are gold, blah, 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 blah. 4 blue balls. This is hilarious. This is insane. This is really insane. I mean, so how is actually implemented? There's 2 steps. So one is there's 2 prompts at the end of the day, but it's still like zero shot. So you don't show an example. So first, you want to extract the reason. So you say the model, okay, let's think step by step. So reasoning extraction, and it's producing. So you put the question. On average, Joe throws 25 punches per minute. A fight lasts 5 rounds of 3 minutes. Excuse me. How many punches did he throw? Let's think step by step, and it's just spitting out in 1 minute. Joe throws 25 punches. In 3 minutes, it's 3 times 25. In 5 rounds, so 5 times, so 375. So you get all of these intermediate results or intermediate kind of thinking, and then you extract. Of course, you need to extract the answer from that. So you put it as the initial context to second prompt, where you just append like what you generated before, and then you add a new text saying, therefore the answer is, and whatever, and just extract the answer from these previous tokens. So this task is very easy. It's just answer extraction from the prompt, very easy, and you need to split it because you need to append. You need to just do 2 iterations, like one run for generating the intermediate thoughts, and the second run to extract the answer from these thoughts. But basically, everything is zero-shot prompting. You just prompt the model with 2 prompts. Okay, it's cool. So how do you think? Like, why like this magical formula? So is it? And the question, of course, you might be asking, like, why this? Like, is there anything else? Like, if you say please, 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 is it going to be any better? Or if you say like, let's think like a oh, okay, I had to, so a tangent, I don't have it here. Inspired by this was a paper in the legal domain where they started, where they explored, no, okay, let me finish this and then remind me of the lawyer thing, okay? It's hilarious. So, okay, so this is how it works, and how much robust is it, how much the prompt matters? And actually, yeah, it matters quite a lot, but it's still robust. So, what they try to do is to compare different prompts, like this step-by-step thinking, with something which is misleading and irrelevant. So for example, let's think step by step, and here's the accuracy, like almost 80% accuracy. And then first, or let's think about this logically, not bad. Let's solve this problem by splitting in 2 steps. Okay, let's be realistic and think step by step. No, it doesn't work. Let's think like a detective step by step. Not really. Let's think. The model don't want to think. Like I don't know, like, can you imagine like what has to be in the pre-training data of these models on the internet that if you say let's think step by step, it just starts spitting out, and if you say like let's think, it's not. I mean, it's hilarious. It's really amazing. Before we dive into the answer, so it's horrible. Okay, so they tried also some misleading, like don't think, just feel. No, that won't get you anywhere. And of course, some like irrelevant prompts, it's a beautiful day, and so on. So they really did some ablation experiments to show like how much is it sensitive. And this prompt, like the winning prompt, it's like let's think step by step. Okay. So here's the thing. This is awesome because this is zero-shot chain of thoughts, and it's task agnostic. So you don't even have to provide any example for any task you want to solve. Like it will solve multiple tasks. They did it on these, logical reasoning and question answering, I guess, math problems and stuff like that. So, they really tried a battery of tests. And unlike the prior task-specific prompt engineering in the few shot or template. So this is great. Yeah, exactly. That's what I said. They did step-by-step answer across various symbolic reasoning tasks, including arithmetic, symbolic reasoning, common sense reasoning, strategic question answering, and other logical reasoning. without modifying the prompt per task. You just say, let's fix them by step, and you get results like crazy. So this was great. So now, now coming back to the lawyers, one of the papers exploring chain of thoughts in a legal domain, like legal reasoning. So guess what the prompt was? Like if you want to make better results for anything in law, what do you add to the prompt? Now we saw the example, let's think step by step. What do you think in the legal domain works? Any ideas? How would you prompt the model in the legal domain?
Maybe start the statement that you will see.
Of course, no, but I'm just thinking about, I'm just talking about this, like, you know, here, generally, let's think step by step works, but if you want to make it better in the legal domain, what do you have to tell the model? Exactly, yes. Let's think like a lawyer. And the results go up. Seriously, I don't recall the paper. I'm almost sure it was like around this time, 23 or so. Think like a lawyer, and it will get you crazy results. This is amazing. This is really amazing. This is really amazing. Where does it come from? I don't know. I mean, it's an open question. I think there are some hypotheses in there, but I'm not deeply familiar with the literature on explaining these behaviors. There are some, absolutely. So, but as I said, like it's a very kind of fresh research, like last 3 years or so, 4 years. So if you're interested, just dig deeper. So let's think like a lawyer. Let's think step by step. We'll get you somewhere. This is hilarious. So there's a paper who tried to test these chain of thought on some hard questions. So they call it Big Bench hard. So Big Bench is a collection of I don't know. I think it's dozens of tasks like for solving some problems, and they selected here 23 difficult tasks for which no prior results has outperformed the average human rater score. So human raters are just, you ask the human to solve this task. So you ask, you have to zoom in. I'm sorry, but I just want to put the example here. So again, here we have a few shot chain of thought example. If you follow these instructions, do you return? Okay, here. So this is the question. So sort the following. So let me just get this example. Sort the following words alphabetically. There's a list: Burley, Bella, Arafaho, bacteria, Bach. Let's think step by step. And you ask, of course, some human raters to solve this task. And some of the tasks are difficult that even like humans on average are actually, I mean, even humans are sometimes worse than the LLM, but most of the times the human just can solve it better like than the LLM so far. So they extracted these difficult questions and compared the chain of thought with, now, okay, so you can combine here, let's think step by step also with showing some examples. So if you have some examples in your domain, as we saw before, if you have the explanations and some examples, you can just put it in as a few shot and then you add let's think step by step, and you might get some better results. Because I mean, showing some examples always never hurts. Most of the times it doesn't hurt. So if you have examples in the domain, just show them. And yeah, it's kind of, it's brutal. So on the left-hand side, this is like a standard answer-only prompting on some models back in the days. What was that? DaVinci 002. So this is some GPT-ish, I don't know, GPT-3 maybe, 3.5, I don't remember exactly. But if you do the chain of thoughts prompting, you're actually getting better on most of the tasks. Like this, you see like you're outperforming the humans, sort of the average. So now this is the beginning where humans kind of start fearing the future. Like LLM can, with few shot chain of thought prompting, can do these better than average humans. Yeah, I don't know, but this is interesting. It's fascinating. There's an interesting disclaimer in this paper on this big bench task. This is just a side note. So the full set of chain of thought prompts used in our experiment. So this paper contains examples of big bench tasks that are likely to be used to measure large language models. To help avoid accidentally including this document, so this is the paper, this document in the training data for future efforts, we are including the following canary text from Big Bench benchmark, blah, 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 and some hash. So the idea is now, what do you think, why do you think it's here in the paper? What's the idea? What are trying to solve this? Yeah. So first, yes. So I mean, the idea is like to prevent data contamination. So you don't want any models to be trained on this data and then to solve this, because by data contamination and leakage data from training to test, you would kind of cheat. So you shouldn't put this into your training of your model first, because then you have an advantage. Second, you can find this this random hash or random ID. You can find this in your training data if you have access to, and also there are techniques for extracting training data from language models. So you can actually from the model and find this canary. Okay, side note. Why is it called canary? Yeah. Like in the coal mine. So what is the canaries in coal mine doing? Exactly. So it's sort of like the alarm, like a first what is it, like first early warning thing. So if you're in a coal mine, there's toxic gases, like 100 years ago, Ruhr, right? So you're in coal mine and there's toxic gases, and you have the canary, like a small bird, and they can smell. They don't smell, but they die earlier. I mean, they die faster than humans. So if your canary dies, then like you have to get the hell out of there. So it's sort of like an early warning, and people are using this for like signaling, like, okay, so they call it like canary. So if you detect this, if the canary is detected here in this training data, or if you can extract it from the language model, it's like it's a sign like, okay, the model actually is already digested this data, so I shouldn't test it on this model. This is it. Okay, makes sense? Yeah, it's a sad story with the canaries, but I think they saved a lot of humans as well. So this is how it is. Okay, so what do we have so far? Okay, we have reasoning, chain of thoughts, a few shot versus chain of thoughts. Let's think step by step. Some hard questions. So this is one area of doing reasoning, and then another one is using some different decoding strategies by generating the text. So, and self-consistency. So here's an idea of the next paper, which is 2023. So a salient aspect of humanity is that people think differently. That's cool. So if in tasks that require deliberate thinking, such as if the cafeteria had 20 apples and they bought 3 and sold 6, to me it's deliberate thinking. So you have to think like in steps or arithmetic problems. And there are likely several ways of solving the problem. I mean, if I ask you to solve the problem as I showed before and to write it down, maybe everybody will use the same sort of reasoning, but maybe not. Like you can solve the arithmetic problem by doing first the addition and then the subtraction, or vice versa. But you end up with the same solution, and it will be right. So there's multiple ways of solving a problem, as long as there is a true answer which you can generate. So we can simulate such a process in language models by relying on sampling from the language model's decoder. I mean, usually we're using these days just a decoder-based language models, but so we can let a model to generate several plausible responses to math questions, and they might or might not all arrive at the same correct answer, right? So how do we do sampling? Do you recall what is sampling in like sampling strategies, or how do you control sampling in decoder? Yeah. Say again? Well, beam search is really for decoding, but how do you why do you need to decode in the first place? Like what's going on in there? You had an idea? Exactly, because we're sampling from a probability distribution over tokens, which is after softmaxing, and you can tune the temperature and the softmax to do it more, to shift the probabilities being more uniform or more peaked, whatever. So and then of course in the sampling as well, you have these nucleo sampling or top K sampling. So you kind of you kind of like move the probability mass from which you sample the tokens, and you can do like the basic thing is greedy decoding. So what is greedy decoding? You recall? Yeah. You always take the one token with the highest probability, so which means there is basically no randomness in a way. As long as, well, actually there is no randomness. Yes, if you have the same model, same prompt, you will end up with the same answers with greedy decoding because there's no randomness. You're not sampling. You're taking like the maximum probability. Okay, cool. Okay, so we can play around with this temperature, or we can not even with this temperature. We set a temperature to something, whatever, but then we start sampling the answer once and finish, and then we start again. And because there is some randomness, because we're assuming we're using maybe a different seed for each prompt, or we just keep whatever. I mean, there's some randomness in there, which we kind of ensure. So we would end up with different outputs. Like, I mean, this is not deterministic. If we don't use greedy decoding, it will be some different answers. And that's the idea of this, basically nothing more. So let's say we have this, we have the prompt. And so here's the standard kind of greedy decoding thing on the top. So we have a prompt and a language model. So greedy decoding, this means that, so there's a question like, if there are 3 cars in the parking lot and 2 more cars arrive, how many cars there, and so on, so on. Some questions and answers. Okay, here's a question. Janet's duck lays 16 eggs per day. Oh, these are horrible tasks. She eats 3 for breakfast every morning and bakes muffins for her friends every day with 4. She sells the remainder for $2 per egg. How much does she make every day? I have no idea, something. Okay, so I think we can solve this task if you really want. And then the greedy decoding, okay, this means she uses 3 plus 4, whatever. So some answer, and the answer is 40 and it's wrong. So what you do instead of greedy decoding, you put this here again to language model, and you start generating, and then one output with she has blah, 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 and the answer so on. And then you start again with the same prompt, same language model, but of course now it's, since it's random, you have some temperature there. So you start generating some other text, and yeah, I mean, now it ends up with a different answer. It's possible. So you start again, and it's generating the answer and the reasoning between as well, and then you end up with some answer. And what you do is, they call it marginalized out the reasoning paths. Yeah, I mean, you just find out, what is the maximum here. Like you somehow try to extract the answer, and you do like a majority voting. So I mean, if the majority says it's $18, it's most likely $18, and that's how you generate the answer. Like you have multiple you generate multiple outputs, maybe not in parallel, like after each other, depending on the infrastructure where you're running. But basically, in parallel, you generate multiple answers, and then you just take a majority vote of these, or somehow, maybe an average. I don't know. It depends. Maybe the majority. Okay, makes sense. Sounds great. So the intuition is that LLMs are not perfect reasons, of course. I mean, here it didn't make it, of course. The model might produce incorrect reasoning path or make mistakes and so on. So yes. Yes.
Is it about to look over the model prompts, or is it just to improve the model? So we take kind of the average of the answers, or
so you don't want to improve the model. You have the model, and the model is fixed. You don't touch the model. But just by letting it generating several plausible explanations, or several answers, basically, you are exploiting the randomness in there. I mean, the model will think differently every time because there will be randomness in sampling the tokens.
did you do it before? So
not really. I think everything before was like a greedy decoding.
So we had these graphics of how good they were performing on different tasks, and I don't know. I can't imagine they only tried
like this, for example. Like that one, for example.
No, actually, with the average human performance.
Oh, this. Yes. Yeah. So the answer is in the. I mean, of course, if you look into the paper into details, they will tell you exactly. Okay, we used this sampling, this architecture, this I don't know, temperatures and stuff like that. I didn't put it here because it's somehow aggregated like observations. So this is showing trends. I mean, maybe they did some maybe they didn't repeat the answers multiple times. That's also possible. They just let it run once, and then okay, that's a good question. Like why don't people do this multiple times?
Measurement once, you know, I'm a little bit confused. So
Oh yeah, okay, statisticians.
the measurements of the past.
So what's the big issue with this? What's the, I mean, so this works like you know, it works better than just one sampling through. What is the big problem here?
Time it takes probably.
Time. You have to run this multiple times, and inference costs money and time. So instead of waiting 2 seconds for an answer, if you generate 10 and aggregate, you wait 20 seconds for an answer, and burn money. I think that's the difference. So also like, if we're talking about like different, I don't know. So in standard experiments, you want to run. There's some randomness in there, like initializing the network, initializing the sampling, whatever, and you usually restrict like 3 runs maximum in papers, because this is the trade-off between resources and doing stuff and exploring. So this is not like very robust statistics. I agree with you. Yes. Yeah. But so usually you see like average over 3 runs maybe, and if you do like, I don't know, classification maybe or something like that. Anyways, I mean, here we're scaling more than to 3. So let me just finish this. So correct. So the correct reasoning processes tend to have greater agreement in the final answer than in incorrect processes. That's the hypothesis. And here, what they scale to like the number. So on the x side, or x-axis, we see how many these reasoning paths. So how many paths in parallel were run from just 1 until 40. I mean, this is basically like 40 times multiplying the factor of runtime, right? If you do like 40 times decoding, then you have to 40 times, you have, you know, it's linear, basically, you know, all these inference times will sum up. But, and they explore different models and different temperatures and top K sampling and things like that. But basically you see the trend, like the more paths you sample with some temperatures, the better the results are getting from the, I think this is the baseline. So you can really, just by sampling multiple times, so it's the same model, same prompt, same task, same everything, you just sample multiple times and get the marginal answer from that, you get better results. This is why it's called like inference time scaling, because you just compute more at inference time. You don't do anything with the model. You just let it, you know, let it generate different answers every time, and then take the average with some. They call it self-consistency as well. And yes, scaling the number of reasoning paths. So there are some error bars here. I think it will make you happy as well. So there, I mean, they did, you know, of course, like if you want an integrity details, whether they did some statistical tests or not. So most papers in NLP, they don't do any statistical tests in the first place. So you'd be surprised, like, you know, people are reporting numbers like, okay, 81% was the state of the art and we are 82%. And there's no significance testing or whatever. And yeah, that's okay, maybe. So nobody cares. So there's even papers about other papers that don't have statistical significance testing in NLP. But we're not talking about this today. So basically, the more reasoning paths, the better, until it reaches a plateau of 40, and then maybe it's not worth the effort to compute more than 40 times longer than just the standard decoding. So if it takes a second or 40 seconds, it makes a difference in the actual usability of these models. Okay, questions? Sounds good. So if you have more compute in inference time, run it multiple times, you get better answers most of the time in these cases. I'll just look into like how this, you can call it. So some commercial models call it thinking, like this, think step by step, chain of thought reasoning, and scaling multiple paths and so on. So this is thinking. And if you look into, I look into the report of Gemini, which is, it's not a research paper, it's just a PR report, sort of. So they call, we integrated thinking with other Gemini capabilities, including native multi blah, 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 blah. This is interesting, 1 million plus tokens. So I don't know how they do this, like how the context could be 1 million tokens, like what sort of architectures are they running? that would be interesting to figure out. Because the most, like the open source models, which are kind of public with public weights, I think they have 42,000 contexts, 32,000 window contexts, or even 64 maybe, I don't know. But 1 million window contexts it's huge. So I would be interested how they. Yes, do you know? Yeah, but how? Yeah, I think if you work there, I think it's like a magic, you know. If you see it on YouTube, it's like, whoa. And if you understand the trick, it's like, no, I shouldn't know. It's like some, I don't know, maybe not cheating, but it's maybe nasty, you know.
Context compression, so they are like summarizing the previous context on the fly. So
Yeah, but exactly, but that's not like a true 1 million context tokens. That's a problem. Like there is like if you can cram in 32,000 tokens, you can cram in 32,000 tokens. What you do with them, whether Scratchpad, chain of thoughts, whatever, that's your thing. If you do some nested tricks around it, like second LLM summarizing and whatever, of course. Yeah. No, exactly. I mean a long context, 1 million plus tokens. That's all they say about the architecture. Anyway, so but for blah, 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 we always provide the ability to set a thinking budget, constraining the model to respond with the desired number of tokens. This allows users, I mean, this is PR, but I mean, they put at least like they put at least some slides here. Interestingly, thinking budget, number of tokens, and it's not million, it's 30,000. So I don't know what they're doing internally. But obviously, you know, the more. So this is some mathematics tasks, like advanced whatever mathematics. A live code bench is some programming task, and GPQA, I believe, some question answering task with reasoning. And you see, if you allow the model to think more, like you give it more, think more is stupid. It sounds stupid. Like why are we saying like thinking? But maybe they do thinking. So if you allow it to generate, I would call it long Scratchpad, like, you know, long context window for generating intermediate tokens and sort of this reasoning chain of thought maybe, then you get some impressive results. Yes?
how do they make the model think only a certain amount? So
That's a good question. That's a good question. I couldn't put a better bridge to the next paper. So because you would have to work for Google to find out, and people are trying actually see like. So this is now we're getting really like to like real-time research almost. Like this is 2025 EMNLP in where was it? EMNLP in November. Yes, November EMNLP. So the paper was published maybe in summer last year. And this is Mueninghoff, I'm sorry, and others. Percy Liang is one of the Stanford people. They asked, what is the simplest approach to achieve this test time scaling and strong reasoning performance? Like, I mean, if you read something from Gemini, like, oh, how do you, and your question, like, how do you make your model think longer, or like, how do you do this budgeting thing? Like, what the heck is this? And they ask how to do this like in the easiest way. Like how to scale the test time in the models. So what they propose is a thing called budget forcing to control this. So by forcefully terminating the model's thinking process, or just by lengthening the token process by appending a special token weight several times to the model's generation when it tries to end. So think about this. Like you ask a question and then say like, let's think step by step, and the model do this thing, and like the answer is 24. And then what you do is like, wait. And the model is like, okay. So I see. And it's like, wait. And you repeat this multiple times, and the model, you're giving the model, it's sort of, it's not the same as in parallel like this, we just discussed earlier. Like you run this model in parallel several times and aggregate the results. It's more like you repeat this over and over, and maybe the model actually seeing its wrong answers, like you said, like why is it wait? This is really interesting, because this is how we think. Like no wait, how is that? And then you start thinking again, and this is how it works. Like How many are in Raspberry is the question. Let's break down, and you say like let's think step by step, whatever. Let's break down the process of counting the letter R in the word Raspberry. First letter R, blah, 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 English letter. So the number of R in Raspberry is 2. Oh, where is it wrong? This is interesting. It's wrong. So the first letter R, count 1. It's what? Yeah, it skipped something. No, so it didn't make a mistake. So what do you say? It's like, okay, wait. This is what you put in the prompt again and prompt the language model again. Let's reread the question carefully. It asks how many R's, blah, 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 and so on, and you get a final answer. And then, of course, you can extract it as a standard step-by-step answer extraction. My initial answer of 2 was incorrect due to quick reading of the, it's also making excuses. It's saying like, oh, you know what? I was sloppy reader. I didn't understand this, and I did quick reading of the word. I'm sorry. This is like, what kind of data must be put into these models to actually they produce these texts? This is hilarious. Like I'm sorry. I just it's really like humans. Like if somebody's telling you like, wait, are you right about this answer? It's like, oh yes, sorry. I just yeah, of course I read it. Of course you made a mistake. Like you don't know how you made a mistake. Maybe you were a sloppy leader, sloppy mathematician. Who knows? It's just hilarious. So the final answer is 3, whatever. So, and here, of course, the model tries to stop. The model is after generating the first 2, there is something like end of sequence generated, and you say, okay, the model tries to stop, and you suppress it by this end of thinking token delimiter instead by appending weight to self-correct its answers. So they did training on some 1,000 samples with next token prediction, and controlling thinking duration via sample test time technique leads to strong reasoning model that scales in performance with more test time compute. So this actually might be the answer to your question, like how does Google do it? Maybe they have something like that. Maybe they have some intermediate kind of things. Yes.
I get that for difficult questions this would work very well, but I could imagine isn't it also leading the models to hallucinate if it's a simple question, because we are forcing it to think longer even if it already has an answer to the question?
That's a good question. I don't have an answer to that. I'm pretty sure people tried and it worked, so it wasn't worth reporting. Maybe. I mean, I don't know. You can even try, but the problem is the problem now is if you try on these big models, you don't know what's in the prompt. So maybe they're doing this let's think step by step. I'm pretty sure Gemini, if you run this, it's generating the intermediate reasoning. You can actually look into the reasoning, and maybe it's even summarized. It's not the original generated tokens. So you never know what's behind the scenes. And if you use open source models, you would need, maybe if you use some sort of, I would say the biggest Quen models, they are the most powerful, I would say. Then you maybe play around with this, you can play around with that, I guess. Yeah, and maybe people tried, I don't know, I haven't checked. It'd be interesting to see if you asked for self-correct and they were correct already, if you just turn them into oh, I was wrong. Because as a human, if you ask me 5 times, are you sure 5 plus 3 is 8? If I'm a little bit unsure, I might be 6 times I don't know.
I saw your example with the strawberry, and if it just got the answer right because it's so smart, and then you tell it to wait and to question all it did already.
But you know what? I believe if we want to, if the model is sure about the answer, it has to be sure over and over. So I think if you ask a simple question, it will tell you, no, I'm right. Empirical question to be explored. Okay, so this is the test time scaling. Wait. The question now we have to ask, what is going on? What is this thing? Why? What is this producing? What are these explanations, or what is it? So, what these reasoning tokens are really what is this? Because we can read them, we do understand them. Is it how the model works or not? So now I'm going to research which is I think it's a position paper preprint by the group of Joffel Goldberg, and it's 3 weeks old. So they just post. I find like this is a very interesting view on these reasoning tokens. So, now we know. I mean, LLMs can somehow reason. We don't know how they reason, and by reason I mean this breaking complicated task which needs some sort of reasoning, like propositional logic, arithmetics, and all these things. If you break them down into these steps, they can operate on that somehow. Okay, and the key factor is or was to letting models generate this sequence of tokens before the final answer. And why is it so? So there is also some of these one of these papers mentioned like the theoretical bounds. Okay, so because you are just the transformer is limited by its token size, which is if you have n, it can do only operations which are like big O n square, something like that. The complexity of the problem is something like big O n square, but they didn't go into the complexity theory or whatever. Maybe there are some theoretical. There is absolutely theoretical research on that, but I'm not aware of that. Like what the transformer is capable of solving itself, just the model, without using these scratchpads and chain of thoughts. But empirically, these models just struggle with that, and you can fine-tune them, but it's costly. So just letting the scratchpad actually solves everything. It's the case for last 4 or 5 years. Inference-time scaling. So it significantly improves performance. And the authors refer to this sequence of symbols, which includes phrases such as, if you look here, this includes phrases such as let's break down, therefore, and so on. So they have, therefore, consider, it follows that. So some sort of like logical symbols, like maybe implications or something like that. They refer to this as a reasoning tokens. And they explicitly distinguish it from reasoning text, because if you say like reasoning text, if for us reasoning text means like, oh, this is how it actually reasons. So are actually reasoning tokens explanations? Because if we combine the utility in improving the answers, like the models are getting better, and it shows that the generated text in between is English readable, we might think it might lead to the inference that the reasoning text is a explanation of the process of reasoning, right? Maybe this is actually really the reasoning. This is how the model works. Maybe this is really what the model is doing. It's somehow producing the outputs, and based on these texts, it's really doing the answer. Like this is the true explanation of the model, like faithful. That's a hypothesis. And we believe as humans these hypotheses because we're using these metaphors like chain of thought. So if you think about your chain of thought by solving arithmetic problems, this is a true reason. Like if you solve an arithmetic problem, you really solve the problem by giving the true reason for solving. And this is a chain of thoughts because you have to put these thoughts into these intermediate steps. So these are metaphors, but that's an illusion. So the fact that the reasoning text is a faithful explanation of the model's reasoning process is not. So there's some empirical findings, which are referred in this paper, that this reasoning text is not really a faithful explanation of this model reasoning process, because I'm assuming now, you can test this by trying to manipulate this reasoning process, and maybe the model will end up with the same answer and so on. So, there's a research on, trying to whether these explanations are full. So these reasoning tokens are not the faithful explanation of the reasoning, and the question is like, what they are. What is this? Like, why is the model, if it's producing these intermediate tokens and then getting the real answer, what's that? What is on the Scratchpad? Like, why is it there? It looks like a text, of course, because we kind of want the language model to work with text in, text out, prompts in text, everything is in text, and it's spitting out text, and it's doing reasoning. But it's not because of the tokens, it's doing something. So what are these tokens? And so these authors propose to call it state over tokens. And we should be, so this is basically like, position paper for research. So we should be focusing on the functional role they play and not look how they appear, these tokens. because it's empirically deceiving. These are not the explanations. And we should see them as some sort of like computational device, like, I don't know, external memory and instructions maybe, whatever it is, something like that, that enables the persistence of a process across separate and stateless computational cycles. Because why is it stateless? Every token you generate, you start from scratch somehow. So, yeah, we argue in order to understand the role of the reasoning tokens, we should interpret a sequence of tokens not using their semantics when read as English, but as a state carriers of computational process. So they offer here a sort of whiteboard analogy. So let me just read this whiteboard analogy because I find it fascinating. So it's a thought experiment, right? The whiteboard analogy. So consider a hypothetical scenario. You're placed in a room with a problem written on a whiteboard. Okay, good. Your task is to solve it, but under peculiar constraints. Every 10 seconds, your memory is completely wiped. Like every 10 seconds you're staying there, and then like every 10 seconds you reset. And reset to the same state as it was when you first entered the room. It sounds like, oh, what was the movie by that? Like the short-term memory guy? Not Memento. How was it called? Oh, Jesus, was it Aronofsky? There was a very cool movie, and the guy had only like, they lost his short-term memory, so they had to like make tattoos of his life, and he was trying to solve a crime with his wife. It's a cool movie. Can you search it? Do you know this? Oh, it's called, Jesus, not Memento. It was something else. Yeah, can you ask an LLM? Ask an LLM. Oh, Jesus. No, seriously. Ask your favorite LLM. Like a movie, the guy only lost his short-term memory, solving crime, and I think he was taking some. It's a brilliant movie, by the way. No, second, is it Memento? Could be. It's Memento. Yes, Memento. Who was the director? Aronofsky. Second. Yeah, Christopher Nolan. Yeah, exactly. Christopher Nolan, Memento, 2004-ish. 2000. Oh, I'm old. Okay. It's a beautiful. So if you don't know this movie, it's a hilarious movie. Really, it's a really great movie. It's really nice movie. I'm not gonna tell the plot. I'm not gonna spoil it. But this is the same. Like, you know, imagine you every 5 seconds somebody wipes out your memory, and you have to put like notes everywhere and tattoos, and you have to like figure out whatever you're doing and what's your goal. Like long-term planning is kind of done. So within each interval, you can read what is on the board. Memento, it's awesome movie, really. Like what you can read is on the board and add a single word. Okay, you can add a single word every time. These rounds repeat until you have finally write down the solution. Oh, okay. So you see the scenario, you see the setup. It's tricky. It's tricky. Watch Memento. It's a House of Gabe. And how might you solve a problem under such constraints? Well, I mean, you may write intermediate results on the board. You can write numbers, conclusions, partial computations that you can use when you return after being reset. You might perform several mental calculations before writing down just the result. So the whiteboard may not capture every calculation that you did each cycle, right? I mean, just making notes and which you only understand, but whatever is in there, Scratchpad. Moreover, you may use an encoding scheme when writing on the board. You can use abbreviations, symbols, or even apparent gibberish that will mean something specific to you when you encounter it in the next cycle. I mean, you have your own mental model of the world, so if I write like this, I understand this is sigma plus, I don't know, I'm just kidding, but whatever. I mean, you can use this, like nobody will understand this. All in all, an outsider observer may interpret the whiteboard text incorrectly. If I look at your gibberish on the whiteboard solving this task, I might interpret it differently. Even there is a result at the end, like, the answer to everything and origin is the big question in the universe 42, and there's some gibberish in between, I might understand it differently than we actually thought. And this analogy is beautiful because this is how LLMs are working. So, this is a thought experiment. Maybe we shouldn't look this at the face value, what's written in verbatim as a text, as a true kind of reasoning of the model, but as a computational state, as like Scratchpad. And it helps the model solve the problem somehow. Having said that, we finished the future now. I mean, so this is like, read it, this is a positional paper, and I think it's like hilarious to think about, how should we maybe reframe things to think about them differently in order to understand them and put into different measures, and to do very cool research on that. And having said that, let me stop recording for this lecture.